Raise your hand if you know what a printed circuit board is. Oh wow, the entire class? Okay, so somebody who, feeling particularly exotic this morning, go ahead and explain it for me. I'm going to point at somebody, so let's see. Somebody I don't necessarily know. Eric. What's a printed circuit board? Speak up, come on. You're lecturing right now. You have a board that has copper on it. It's like putting wires on the board. That's a very good explanation. Thank you. Everybody, round of applause right here. Come on, yeah. Boom! Best lecturer out there. All right. So basically, exactly what he said. It's a piece of fiberglass. Generally, not always fiberglass, but typically fiberglass core with copper inlays. Again, not always copper, but the vast majority of the time it's copper. I'm going to talk to you guys about 99% of printed circuit boards out there. For any of you who have done internships in manufacturing technologies or are aware of specialty types of printed circuit boards, one, I'd love to talk to you because this is probably my favorite area of engineering. And two, I do realize that there is an exception to literally every rule. But typically it's fiberglass with copper inlays. Traditionally either one or two layers of copper, so you have a single core of fiberglass and then you have copper on the top and copper on the bottom. That copper is etched out in such a way that they become wiring connections. I'll talk a little bit more about that in a second. Printed circuit boards can contain built-in elements such as antennas or heat sinks into the copper. So this copper that's laying all over the board, it can be used to wick away heat, or it can be used to transmit RF energy, or do all sorts of things. But most typically, what you see a printed circuit board for is basically to replace what your breadboards do right now. So what it is it's a single board that is design dependent, and it is wiring up the chips that are currently resting on your breadboard in one very specific way. And the reason we do this is because you don't want to put breadboards into final products. Can anybody tell me, which I've already told you a bunch about, so hopefully somebody can recap the lecture, can anybody tell me why you wouldn't want to put a breadboard in your final design? What's one thing breadboards have that other things like printed circuit boards don't? Raise your hand. There's a bunch of things. Terrible parasitics. That's probably on my top three. I would say top 3 reasons why you don't. So that's one. Anybody got another one? Yes, there we go. That's probably my favorite one. That's probably my top. Wires fall apart. Okay, printed circuit boards are less likely, they can, but less likely to fall apart, especially due to things from like vibration or something like that. Anybody want to give me one more? This one's big. Although you guys might oversee. Yep. Noise. Noise kind of goes hand in hand with the parasitics thing, but I like it. That's another good one. The one I was actually looking for on my top 3 would be size. Breadboards generally are going to be a bigger circuit. Printed circuit boards can do surface mount components as well. If any of you, raise your hand if you haven't heard about surface mounts. Okay, that's great. Real quick, everybody needs to click in, by the way, I forgot. So, standard frequency, BA, and then everybody click in. And again, please use the spectrum A to E, so if I start to lose anybody, if you guys don't understand or you don't want to ask a question, but you're still kind of lost, go ahead and just press E on your clicker, and you can do this at any point throughout the lecture. Oh wow, I've got people pressing E already. Is there a topic that I don't understand? Raise your hand if there's something you don't understand or have a question about. Okay, then I'm sorry for the 3 people who have pressed E, but because you are shy and timid and don't want to ask a question, we're just going to keep moving on. So, moving on, PCB alternatives. Well, there's all sorts of cool alternatives. This is your standard breadboard. I think everybody's familiar with this technology. Some students aren't aware that breadboards come in different shapes and sizes and spacings and stuff like that. They're not as common as your standard breadboard, but breadboards can come in different situations. So, yeah, you should be aware of that. This right here is called solder board. Now, you may also hear it called proto board. Proto board is actually a portmanteau of prototyping and board. So, proto board can really be anything that's designated for a prototype. Traditionally, not a printed circuit board. A printed circuit board is normally used when you somewhat finalize your design. So, proto board can be interchangeably used for both a breadboard and a solder board. Everybody here has seen a solder board, right? Press E if you haven't seen a solder board before. Okay, so actually a fair number of students have not. So a solder board traditionally is this color right here, and what it is it's got copper on the bottom of it that looks exactly like your breadboard. The only difference is that it has to be soldered on instead of plugged in. Okay, so the copper on the bottom doesn't make a connection until you actually solder your components to it. And then once you solder your components to it, that design becomes a little bit more finalized. The benefit of using solder board over something like a breadboard is you deal with the fact that things don't fall out. And that's a huge benefit to you. However, you aren't going to be able to get as condensed as a printed circuit board, and your components are still very much in a linear pattern. This can be design constraining in some situations. So there are benefits and detriments to solder board. Somebody press E, or I don't care. Somebody raise their hand if they know what this is, right here, other than Dr. Ferguson, who I would imagine doesn't know what this is. Anybody know what this is right here, the picture on the far left? There's a zoomed in picture on the bottom left of that picture. Anybody seen this before? Anybody here intern for NASA? No? So this is actually wire wrapping. Okay, what this is it's a very small wire that you actually wrap around each individual pin of your circuit. This was an older technology, really had its big days in the 60s and 70s. However, it's still used by most space agencies. And the reason that is because the amount of mechanical stress that you can exert to a wire wrap circuit is significantly greater than even printed circuit boards. So this is one way. However, I do want to mention to you guys that it's a wire between every single connection. Realize what that looks like when you're done. It's a rat's nest. It's impossible to debug, and it's possible, but it's very hard. They had robots that would do it for you. So after you had laid out all of your components, you could put it on what was called the perk board, which was just holes, no copper, but looks very similar to a solder board or a breadboard. Just holes. And then they would have a robot that comes in and would wire wrap all the wires for you. But then if there was something wrong with the circuit, your odds of debugging it were slim. It is possible. And they had different debugging techniques. But this is something you should be aware of, and for those of you who end up going into, space, or, end up designing circuits that go into space, hopefully you can come back one day and tell me all about how you learned about wire wrapping. Or, I am aware that certain low-G space material will use printed circuit boards now. The technology has progressed very quickly. Printed circuit boards have advanced leaps and bounds just in the last 4 or 5 years. So the material on here is just a little bit outdated. All right. PCB design flow, schematics. We've already covered schematics. If you guys have more questions, you're always welcome to ask. Again, these are some of my favorite topics to talk about. Manufacturing is just one thing that I've always loved about engineering. You also have electrical rule checks on a schematic. This is how you verify it. You have layout. This is printed circuit board layout. We're going to be talking a little bit about that today, and I believe we'll be talking about it next lecture as well. You have a design rule check. Design rule check is different than an electrical rule check. A design rule check verifies the actual circuit that's going to be printed on a printed circuit board. Again, I'll be talking more about that later. And then fabrication outputs. These are the files that you send to a company to actually manufacture your printed circuit board. All right, ERC. I've covered this before, right? What an electrical rule check is? Anybody remember? Somebody want to raise their hand? Tell me what an ERC is? Okay, electrical rule check. This is something that you run on a schematic, and it will tell you what is wrong in your schematic. So, for example, if you have the output of a LM393, a standard comparator, right? But the standard comparator, the LM393, has a strange attribute about it. It doesn't have an internal pull-up resistor. So it can only switch between the states of ground and high Z. So if you don't have a pull-up resistor wired externally to your component, often an electrical rule check will correct you and say, hey, you might have forgotten a part. This is important, or else your circuit isn't going to be able to do anything. Or if, for example, you have the output of one chip connected to the output of another chip. An electrical rule check will often tell you that, hey, on your schematic you have 2 outputs. There is a potential problem here. Now, it is possible to connect up outputs to outputs if you do proper handshaking and signaling, but most schematic electrical rule checks will will go ahead and warn you about potential problems. And then there are also electrical rule check errors. For example, if you have all of the power and grounds wired up on your schematic, but you don't have any headers in the schematic to put that power and ground into, because when you put power and ground on your schematic symbols in something like Altium, PSpice, OrCAD, all that stuff, that's a symbolic power and ground. That gives you no physical place on a board to plug things in. So keep in mind, a printed circuit board at the end of the day is something you hold in your hand. It's something very real. You have to be able to plug in everything everywhere. And so if you only have symbolic stuff on there, it'll throw errors and say, hey, you can't really manufacture this board because it's meaningless. So it keeps you from making bad boards, typically checks power and ground, ensures components have values. That's an important one. Now, a lot of students will say, well, why do all my components have to have values, especially if I gave them all unique names? Well, it's because traditionally, a printed circuit board is not populated by the engineer who made it. Now, you guys are in a class, and we're simulating, a real-life scenario, so we kind of have you play jack of all trades. But in real life, the way this traditionally real life, you guys are living real life. But in industry, traditionally you have a designer who designs a circuit. Then you'll pass it off to a printed circuit board technician, depending on how big the company is. Smaller companies, traditionally, you'll also have the person who designed the circuit also be the one who lays out the circuit. This is often called a layout engineer or layout technician, and they will take your schematic, look at all the components. They still have to know quite a bit of the design. I mean, we'll get to this later on, but if a certain element of your design is extremely high frequency, you have to make sure to shield it properly when it comes to the printed circuit board. So you hand it off to a layout technician, and then the layout technician will send it to a board house. The board house fabricates it. None of you guys will be fabricating your own boards. Board house will fabricate it, and then you have another guy who's an assembler, and the assembler takes all these chips that he's been given, he plugs them into the slot where the chip name matches up, and he plugs it in. So the reason that it forces you to have all your components labeled is because normally the guy who's making the board is not the one populating it. It is something we will force on you. You have to label all of your components, both names, and I don't care if it's just R1, R2, R3, as long as they're all unique names and values. This is because it makes it a lot easier in case something goes wrong in your printed circuit board, to be able to look at it and say, okay, this is how we're going to debug it. It makes sure that outputs are not directly connected together. Again, sometimes this can be allowed in your guys' particular project. There would be no reason why you ever need to connect outputs together. So this is traditionally a warning on most ERCs. Then it checks to see if you have shorted capacitors or resistors, things like that. I think it's pretty obvious why you don't want to short across a resistor, because then why is the resistor there in the first place? Although there are reasons to do that, but we'll get to that later on. That's a printed circuit board specific thing. So a lot of times if you want to have a wire in between a resistor because you don't know if the resistor is going to be there or not, you can actually cut the wire and then the current is forced to go through the resistor. A common technique if your design isn't 100% solidified. It also makes sure that the schematic is visually readable. So it'll try and make sure that all the text isn't under wires or underneath another IC. All right. This is an example of an ERC from Altium. It has a bunch of errors and warnings, and it's going to tell you what they all are. So if we look right here, this is what the message is. I'm not sure how well you guys can read this, but I'll read off a couple for you. Unconnected net on pin RA1-5, and then it gives a grid location, okay? RA1-5 in this case was the name of a pin on an IC, and it hasn't been connected up properly. So Altium is going to throw you a warning for that. I'll read you off one of the errors. Net TCK contains a floating input. That's a clock input. So the ERC checker knows that your chip isn't going to do anything without it being clocked. So it's going to throw you an error and say, hey, you need to really pay attention to this. You can actually configure in Altium what is considered a warning and error allowable, all of which have different hierarchies. I was close friends with somebody who worked at a company designing printed circuit boards, and actually they were at the point where if, unless you had been working for the company for, I think it was 20 years, you weren't allowed to submit any printed circuit board that had a single error on it. And then if you had been working with the company for 20 years, you had to submit a report why that error was allowable. So generally, if you see an error on your ERC, there needs to be a good reason why you're allowing it. Warnings are less so. something normally can be a warning and allowable. But errors typically on most ERCs by default are something that has gone horribly wrong. You're not ready to move it to PCB. All right, this is ERC on the program Eagle. Both are available to you in lab. We highly suggest that you use Altium. Our TAs are trained a little bit on both. Both Dr. Slavy and I are both trained on both of these programs. We'll be able to help you out quite a bit with both of these programs. So yeah, that's why you'll see a couple of comparison slides between Altium and Eagle. So both are made available to you. So for example, this person has no errors on their board. A couple of different warnings. A power pin V+ is connected to plus 15 volts. So that's where the pin on the package is named V+. It expects to be connected to a net named V+. So the fact that you named the net being the wire, by the way, the fact that you named the net 15 volts, plus 15 volts, threw it off. But this would be an allowable error. That's fine. Then it also throws some warnings down here. Parts C1, C2, C3 have no value, so some unlabeled capacitors. Missing junction in net PE. So here you have wires that are crossing each other, but don't have actually the dot on it. So it's actually making sure that the schematic is readable by a human, which is important. Everybody go ahead and click in. I want to make sure I haven't lost anybody. So A through E, how you're feeling about the content that I'm presenting right now. Okay. Cool. I haven't lost many people. Some people are kind of in the middle, but that's all right. I think we're going to keep moving on there. Objective. What is the goal of the hardware design process? Well, it's designed to connect up your circuit in a way that's going to meet all of its requirements. So here's a picture of a couple of printed circuit boards. The one on the right actually is going to be a little bit easier to see. So here you can see this is copper, this lighter green area. And then the darker green area is where copper is not. And here you're connecting all of these points on a board. So just to give you a feeling for what these things look like. What does it look like when you manufacture PCBs? Well, there's a multi-step process, and I think I have some pictures of it. I do have some pictures, but it's later on in the presentation. Here are some steps in the process. So first thing you start out with is you start out with a piece of fiberglass that is coated with copper on both sides. This is called substrate. Typically, the substrate you'll use is FR4, stands for fire resistance value 4. So printed circuit boards came from a time where the biggest concern with electrical circuits was how quickly would they catch fire. Not really the concern as much anymore, but still generally a concern. So printed circuit boards, kind of through legacy, through history, have been rated, the substrates have been rated by fire resistance. So back in your old 2 boards when you were carrying, hundreds of volts at, potentially half an amp or so, that's a lot of wattage, a lot of heat. And so you would have to worry about this stuff with fire. FR4 is designation means that it is significantly less likely to catch fire. It also has adapted, FR4 now kind of pseudo refers to a lot more than just a fire resistance value. It also has to do with a defined, okay, get off your phone. I'm looking right at you. Is that your phone? That's not your phone, is it? That's your clicker. Oh, I feel bad. Aw. I'm sorry. Don't be on your phone. Anybody. Thanks. Sorry. So, you start out with the base material, fiberglass, covered in copper. You etch it away with acid. And so this etching process I'll talk a little bit more about in a second. There's a way that you can stop the acid from eating away copper in different areas. Then you drill your holes. Then you do through-hole plating, which puts metal in between those holes. Then you do solder mask application, silk screen application, and then electrical testing. Electrical testing is marked as optional. Most of you guys will not be paying for electrical testing, but if you were a professional manufacturer where you're shipping thousands and thousands of circuits, one thing you want to be able to do is verify that every single connection that should be wired together is wired together. So they have robots that come in and basically do a beep test. You guys remember the beep test, right? Everybody shake your heads? Yeah. Okay. It's a robot that basically does a beep test over and over again between all the points on the board that should be connected and make sure that it beeps for you. It doesn't actually beep, by the way. So, yeah, disappointing. Base material, you have a PCB blank, again, generally called fiberglass substrate. You have a resist. This is a material that stops the copper from being eaten away. And then you have an etchant, an acid that generally dissolves the copper. Resist, some of you guys may have actually heard of hobbyists using toner paper. Has anybody ever heard of this? Raise your hand if you've heard of this, using toner paper for etching PCBs. One person in the class. Wow. It's really cool. But you can actually make printed circuit boards at your home, buying etchant from Radio Shack and using some toner paper and ironing it onto a copper clad board, and then sticking a copper clad board into the etchant and having it remove all the copper that isn't protected by the. Okay, so this is the etching process. You take a negative image of your circuit, so in this case, look at how all the wires that you would want to be connected are black. In this case, this is a negative image of your board. You apply it to a copper substrate, and then you expose it to the etchant solution, and the etchant will eat away all the copper that is exposed. And then it goes through, and it drills. The holes that connect layers between layers that are not pads are called vias. Via, obviously, the word means by way of, but a via is an element on a printed circuit board that moves from layer 1 to layer 2. So real quick, I want to make sure nobody's, because this is generally where I lose students, so you guys click in, make sure that I haven't lost anybody. And I'll be monitoring this a little bit more closely now. So you have a copper board on the top, has wires between points, and then you have a copper board on the bottom. One thing you can do in a printed circuit board program is you can move from bottom layer to top layer. And what it does is it drills a smaller hole, and it puts metal in between it, connecting the top and bottom layers. And this is called a via. All right, nobody's lost, so I'm going to keep moving. To ensure electrical connection, you have a ring of copper that's larger than the hole, and it's called the annular ring. It's exposed copper, so if you look right here, even though this doesn't have to be exposed, it generally is. What that allows you to do is if in case your through hole didn't plate all the way through, you can still stick a wire through there and solder it. So solder mask, the green stuff on most printed circuit boards, resists solder chemically. It's a chemical reaction. Resists solder, stops the oxidation of solder. And so what the exposure of the pads here does is it allows you to solder onto those points from the top. All right, so drill plating. This is, again, just going on a little bit more about vias, so I think I've covered that material pretty well. Solder mask. Solder mask is the overlay on top of the printed circuit board where you don't want solder to be. Okay? So it's going to resist solder being attached. So on most of your printed circuit boards, when you get them back and you're trying to solder, and you're trying to solder next to the green stuff, okay, generally the solder is going to avoid jumping over the green stuff. It's going to try and stick to the area where metal is exposed. Solder mask can come in different layers, and then you have another layer called silkscreen. This goes on top of solder mask. I think the next slide is, no? There we go. Here's actually a picture of the process from beginning to end. So here you have a base copper substrate. Here you have an etchant applied to the entire board. The board was then dipped in acid. There are not pictures of that. And removed. This is the board after it has been etched. Then they apply a solder mask, the green stuff, right here. And then you have the finalized board with silk screen. And this silk screen is awful. There's a note over here. There's missing and overlapping silk screen. Do not use this as a reference, but the rest of the process pretty much. We can go back to the next slide, previous slide. This is electrical testing. So again, like I said, you have robotic arms. They come in, kind of tap all the points that you want to have tested, and it's basically just running a very small amount of current from point A to point B, and it's making sure that it can properly pass current over and over again. And one thing they will do generally, if you have many, many robots coming in at once, is they'll actually throw in a very small amount of alternating current of a very specific frequency, and then what the robot does is it reads the amount of current running through at the other end, and it wants to make sure that they all match up, and this makes sure that not only is everything connected, but also not everything, nothing is shorted. So that's another important thing to know. Make sense? Everybody following? Nod your head yes if you're following. Nod your head yes if you're bored. Nobody. Wow. Okay, I got one guy. One guy's willing to admit he's bored. This is exciting. You should be pumped. Who's pumped? Come on. Woo! There we go. Yeah, somebody's pumped. I'll give it to him. All right. So once we're done with that, how do we make printed circuit boards? So now that you guys understand the process, beginning to end, and hopefully you do. If you don't, I love to answer questions about this topic, by the way. So you guys are always welcome to email me, come and talk to me. It's probably, I have several books on printed circuit board process and standards behind printed circuit board manufacturing and stuff like that. It's just a hobby of mine, really. So anyways, there are tools that you use to create printed circuit boards. These range in price and quality. So you have tools. Most of you have used Altium at some point. Raise your hand if you used Eagle, ever. Some of you took 362 and used it. I know that, right? 3 of you that raised your hands, you guys did in 362, I assume? No? Where'd you learn it? There we go. Start challenge. Yeah. So anyways, we have lots of tools. Each of these tools is a little bit different, but they're all trying to do the same thing at the end of the day. They're trying to get you to a printed circuit board. KiCad is completely unrestricted, free, open source software. We do not have it installed in the lab, but you guys can go home today, install it, and check it out, and do cool stuff with it. None of you will, but I would be really happy if one of you did. KiCad's a pretty cool program because it's entirely open source. All the code is modifiable, and you can configure it however you like, and you can start designing printed circuit boards from home very easily. Eagle is also a common tool used by people trying to get started. It has a free demonstration version. It will allow you to design printed circuit boards up to the size of an Arduino Uno for free. They chose that because the development of our Arduino was done on Eagle. And so one of their demonstration boards actually is the Arduino Uno printed circuit board, is one of the demos that you get when you install the program. And so they want people to design shields for their Arduino and all that stuff on Eagle, which is why the free version allows you to go up to that size. Eagle is very well community supported. Probably the easiest to learn PCB tool that I've ever learned. I've learned quite a few PCB tools. I've tried my hand at quite a few. I've done Design, Spark, OrCAD. I'm not going to count them out in front of you guys, but I'd have to guess it's probably around 7 at this point that I've tried my hand at. Eagle was the first one that I learned to use on a professional level. Has a huge community support. Altium, though, is probably my favorite tool, and the reason Altium is my favorite tool is because it is by far the most powerful tool. So those of you who go off to more advanced institutions like Intel, Northrop, or Boeing, or the big companies, they'll traditionally use tools that look at least a lot more like Altium if they're not using Altium, the exact same tool. And the reason they do that is because these tools can support very large boards with very complex structures. If you have many data buses on your board, a bunch of different voltage levels, and you're doing it all on one board, you want to make sure that you're able to keep track. And it starts to look more like an EDA suite more than just a printed circuit board tool. So Altium is probably my favorite tool. It's installed on all of your computers. I highly suggest you guys use this tool, one, because you should have a limited experience with Altium from 208 in the simulation side. And the tool does not change that much when we go into PCB layout. All right. What's the design process? So programs like Altium and others like it, they'll often represent a symbol and a footprint. A symbol is what you guys have used up until this point. This is what's represented in this schematic. So for example, if I put an AND gate in the schematic, I'm normally going to get a 3-terminal device, right? Everybody shake your head, you guys are familiar with it. This is an AND gate, 2 inputs and an output. But that is not what an AND gate looks like in real life, right? You guys go grab a 74HC04? No, 04 is an inverter. Somebody help me out. 1, 0, right? It's an AND gate. Anyways, it doesn't matter. You guys go grab an AND gate, okay? And it's got, 16 pins on it, I think? 16 or 14 pins on it, okay? Because it has multiple AND gates inside that chip. That chip is called a footprint. What that chip can plug into is called a footprint. It is represented in printed circuit board mode. This would have been a great time for a picture, and I didn't put one on there. So notes for next time, put a picture on there. But a footprint is what the chip is actually able to plug into, and symbol is what it's represented in. Part libraries are available online. So for Eagle, they're all over the place. Part libraries, there's a couple of formalized ones. So Eagle comes with standard libraries. All of those are tried and true. They're good libraries. SparkFun has a good Eagle library. Those are also very good. But then after that, you'll often find libraries that have like a single part piece in them. They're hard to find, so you'll have to create parts after that point for the most part. That's what I do. Altium comes with, I would say, actually a fairly limited initial library. But if you go online and download the Altium 9, version 9 libraries, you'll find that they have a huge array of simulatable, usable footprints that contain both, libraries that contain both symbols and footprints. Very useful libraries to download. So you might want to bear that in mind. There's tutorials online for both of your supported softwares. If you guys have any questions about how to use the software, always feel free to ask myself, Dr. Swavey, a TA, your professor, whoever it is. If they can't answer your question, they'll probably direct you to somebody who can. All right, parts, tips, and tricks. So, a lot of parts contain many functions on a single pin. Most commonly, you're going to run into this with microcontrollers. You need to make sure that you wire up the pin only for the function you've assigned to that pin. So, for example, if you have a single pin on a microcontroller, or your CPLDs, this is a better example. CPLD. We borrowed these slides off of 477. The CPLDs, you can have a single line that might be able to work as a UART. It could be used as an I2S output. It could be used for a bunch of different things. You can't wire it up to everything, okay? So you can't simultaneously make one pin be a UART and a GPIO and I2S. You have to pick something, assign that pin, and make it that permanently. Some of you are smiling, almost laughing. Trust me, I've seen students do this before where they think one pin can constantly be everything all at once. That is not entirely true. You need to make sure always to connect all of your power and grounds. This is extremely important. Okay, so a lot of chips have more than one power and ground. It'll have multiple. The reason they do that is throughout the die, a piece of silicon inside the package. I'm going too deep into this. You just have to make sure to connect all of your power and grounds. This is a very important aspect, and when it's on the die, doing proper power. All right, ERC. We talked a little bit about this before, but you want to make sure that these general schematic tips and tricks, you need to run it, okay? So a lot of printed circuit board tools. In fact, all of them that I've listed on this lecture, and all of them that I've used in the past, they will allow you to go directly to PCB without running ERC first. Do not do that. You are digging your own grave there. If your schematic is not passing ERC, if you have errors on your schematic, odds are you're going to start routing a printed circuit board that is bad. It is a bad printed circuit board, so you're wasting your time. Signals can often be connected by giving the net the same name other than instead of just connecting wires between them. If you do this, make sure you indicate it visually somehow. So in Altium, they have the net name command that basically puts a label above a net. And in Eagle, they have a label command, and labels do the exact same thing, only they put an element on your schematic. This makes it so that we can read it. So for example, if you have, an ADC output or an I2S output, that's more applicable to you guys, and you're referencing it in a bunch of different places, and so you didn't want to draw the wire between all those places, what you need to do is you put a little label on each net that is the I2S line, so that we can look and read the schematic and say, even though it's not connected by a wire, I can see that this net and this net are the same thing. This is important. Junction dots, I've talked about this before, right? Shake your head, yes. Everybody? Yeah? Okay, junction dots. Do proper junction dots. This is what a PCB layout looks like. We'll be talking a little bit more about this. I'm not sure if it'll be next lecture or next Monday, but we will be talking more about layout. But this is just a broad overview of printed circuit boards as a prep for the next lecture in the series. layout needs to be done carefully and will often be done in iterations. So think of it like writing paper for an English class. For those of you who did your English classes the way your instructor wanted you to, you often write up a draft, and then you revise the draft, and you revise the draft, and then you have a final product, right? Everybody familiar with this process? Standard writing style? Okay. Printed circuit boards are done in a very similar way. So you'll do it once and it'll be wrong. I promise you. I have never once, my entire academic career, my entire career as an instructor, never once heard, not even just seen myself, I've never once heard of the first time a student laid out a printed circuit board, it being done correctly. Okay? There are a lot of steps in this process. There are a lot of places where things can go subtly wrong. And things that, they really are gathered from just a little bit of experience goes a long way when it comes to printed circuit board layout. And so most of you, when you lay out your board, it will be wrong the first time. So you will have to go back and rewire it up. That's okay. Everybody does it. But what I don't want you guys to do is draft it up once and say, okay, I'm done, and send it off to a board manufacturer and be done with it. We had students, in fact, we had an entire semester of students, partly due to lack of proper oversight. We had an entire semester of students who really fabricated the first boards that they manufactured. All the students bought printed circuit boards, and none of them worked. And I don't think that semester we had a single student who actually presented with their printed circuit board. Do not send out your board unless you've had it checked by a TA, a professor, or somebody who knows what they're looking at, okay? For all of my teams personally, by the way, I want to see all of your printed circuit boards myself. Terminology. So, what is a pin? A pin is a place where you connect a part, okay? So if you have, your 74 HC04, that's an inverter, but we'll go with that. You plug in your part, and the holes you plugged it into are called pinholes, okay? These are different than vias, which are a different part. A pad is the name of the hole that's actually there. So pin on the chip, pad, what's on the board. Via is connecting two layers. What's a trace? A trace is a wire, okay? It's one-dimensional according to the software, okay? Now obviously in real life it is slightly three-dimensional, but it's mostly flat, okay? And it's connecting two different points. A signal plane is traditionally two-dimensional. It lies on a single layer of the printed circuit board, and it can connect many things at once. We'll talk a little bit more about those. Either have a slide here later, or we'll talk about it later on. Oh, okay. I need to do something. We've had a couple of students walk out of class. I'm not a nice person. Everybody go ahead and click back in again. The number was 63. Let's see how many we lost. For students who walk back in, go ahead and remind them that they should click in. Wow, we lost 10 students? Oh, less. Okay. I'll take 5. 5 is anyways, so signal plane connects many different points at once. And a mil, this is a unit of measurement used in printed circuit board technology. This is not a millimeter. Okay? A mil is 1,000th of an inch. Okay? So, yeah. Stands for milli-inch, by the way. So, if metric imperial lines weren't already obfuscated to you, I'm going to obfuscate them more. Alright. Layout. Every printed circuit board manufacturing house has tolerances. They can only make something so small, or so big, or so thick, or so thin, okay? They have minimum things that they can do. So everybody, you want to click in again, by the way. Click something. For those of you who are going to be ordering printed circuit boards, you will be very interested in knowing what these are from the place that you order. These are general tolerances that I have pulled from a slew of different board houses that I work with. I have many, many different board houses that I've ordered through. I'm fairly familiar with most of their tolerances. This is a good rule of thumb. So, drill tolerances, plus minus 5 mils in diameter. That means when you specify that you want your hole to be 1/4 of an inch big, Well, quarter of an inch, you generally think 0.25 is an inch, okay? But because the tolerance is plus minus 5 mils, it could range anywhere from 0.255 to 0.245, okay? This is traditional. You guys have to keep in mind that there is a percentage of error involved with anything in the real world. Printed circuit boards, when you're manufacturing them, they will tell you exactly how much percentage error is in everything, okay? And so, and by the way, in this case, it's not a percent error, it's just a solid amount of error. There's a possible layer-to-layer misalignment, okay? So when you put your top layer on top of your bottom layer, sometimes they'll get offset just a little bit. You have to be aware of how much they can be offset, all right? Now, the question becomes, how do I check for all this stuff at once? The good news is that you don't have to. All of the software that I've shown you guys all has the ability to program in tolerances, and the software will check it for you. So for example, if your layer-to-layer alignment is 3 mils, okay? And you're connecting the two layers with a 3 mil diameter hole, okay? If you get the maximum offset, the holes no longer line up. Does everybody understand what I'm saying right now? You see that? Click in. Press E if you don't know. Okay, a lot of people don't know. So, I have a top layer right here. It's got copper. If I were to look at it from the top, I see wires moving around, okay? So right now we're looking at it cross-sectionally. It's got a top layer. And I have a bottom layer. These guys connect through holes that you could see if you were looking at it from the top. But now we're back over here. There are holes that connect the two layers. That hole were 3 mils, okay? 3 mils in diameter. That's supposed to connect the top layer to the bottom layer. And our maximum layer-to-layer air is 3 mils. If I were to offset a 3 mil trace by 3 mils from the top layer to the bottom layer, they're no longer connected. So everybody click in again. I'm really just looking at the E's here. And there's only one person out there who may or may not still be here, who knows, who did not follow that, so I suggest you ask your classmates. So, layer-to-layer alignment. Etched feature size. This is how small of an area can you etch out. In this case, they give a two-dimensional parameter. Some board houses will give you, or a one-dimensional parameter. Some board houses will give you a two-dimensional parameter. This is normally one of the smaller parameters they're given, by the way. Something I generally do not concern myself with too much. Isolated trace size. This is as small as you can make a trace. The wire that connects two different points is 6 mils. Now, just because you can make a trace 6 mils does not, pay attention, does not mean you should make a trace 6 mils. Anybody raise their hand and tell me why they think making a trace between 2 points really, really small, really, really flat might be a bad idea? Current. There we go. So actually, I'll have to do it for you guys. I do it every semester. I don't know why I didn't even think to bring it today. But I bring in a car battery and a printed circuit board. I'm going to pump some current through some traces, and we're going to see how big those traces should be. Okay? So when you're shorting a car battery, your traces need to be huge. Okay? And so the traces will literally pop off the board. Okay? You'll watch copper dissolve right in front of your eyes. So you guys have that to look forward to. Probably the next time you see me up here. Okay? And so you have to make sure that your printed circuit board can carry the amount of current that it needs to. How do you do that? There are calculators online. It's fairly simple. So you can go online and you can look at trace width calculator, and you tell it how thick your trace is, how wide your trace is. So again, keep in mind they're not actually completely flat. They're differing amounts. So the way they're classified is in a single square inch on a printed circuit board is there 1 ounce of copper, 2 ounces of copper, or half an ounce of copper. Does everybody see how specifying that would change the thickness of the copper in the third dimension? Click in. I want to make sure everybody's following what I'm saying. All right, still got some lost people, so I'm going to try one more time. That's what I was worried about. You have a layer, okay, of copper, and you're pouring copper over this layer, okay? So in this case, it's a real piece of fiberglass, pouring copper, okay, liquid copper over fiberglass. if I take a square inch after we pour copper, assume the copper spread out uniformly, it's completely even. If I cut out a square inch, and I were to measure how much copper was poured in that area by volume, okay? 1 ounce copper would be half as thick in the Z dimension here as 2 ounce copper. Everybody follow what I'm saying? Shake your head if I'm making sense. Now, all of you E people, if I explain that to a point where you understand, wow, that number's going down fast, so I'm going to keep moving on. So, yeah, you always want to consider the thickness of your copper. So that gets put into a trace width calculator, how thick it is, how deep it is, and then also how much current it's supposed to come through. As well as most trace width calculators will also ask you if it's on an internal or external layer printed circuit board. Now, I've been talking about printed circuit boards as if they were only 2-layer devices. That's because most of you guys will only be designing 2-layer printed circuit boards. But you will find in real life, printed circuit boards can range anywhere from 2 layers to 256 layers. I have a 256-layer printed circuit board. It's probably really expensive to manufacture. And so the internal layers are traditionally used just for proper power and grounding, and then also some high-frequency signaling. The reason a trace width calculator asks you is an internal or external layer is because it wants to know exactly how much heat is going to be dissipated. If you're on an external layer, you're exposed to the air and the environment, so you can wick away heat a lot faster. If you're on an internal layer and you're surrounded by lots of copper and fiberglass and all that stuff, you're not going to be able to wick away heat as fast. So if you remember back in the beginning, I was talking about you can put heat sinks and antennas on a printed circuit board. If you're trying to heat sink with a printed circuit board, you won't be able to do that with an internal layer, okay? Because it's not going to be able to wick away. All right, what do we have left? Layout guidelines. You generally want to keep your traces 10 mils apart from each other. Power and ground traces almost always should be your largest traces on your board. Out of those two, does somebody want to guess which one would be larger? Out of power and ground. Here's a hint. Many boards have multiple powers, but only one ground. So which one do you think would be larger, ground or power? Ground, because it's carrying the current from both the powers. Okay, this is an important thing you have to keep in mind. Everything always is trying to return back to ground. The ground is traditionally the first trace you'll route in a printed circuit board because it's the most important. You route from most important to least important. Will traditionally be the first trace that you wire up, and you will also normally be the thickest. Yeah, I'm just going to skip through this. I want to actually finish this real quick. DRC will quickly check your boards. You guys, I have 5 minutes left, so come on. Yeah, 5 minutes. That's what we're going with. I have DRC will mechanically check different tolerances throughout your printed circuit board. This is just as important as DRC for schematics, but what this does is this is your final check, okay? Your TAs and I will look over your board, but we can miss stuff. The software does not miss stuff. As long as you have programmed the software correctly, you have told it all your tolerances. If you screwed up something on your board, it will tell you. Okay? I'll jump through these. This is how you order boards, a couple of common manufacturers. I highly suggest you look at the website PCB Shopper when you go to order. Turn time, shipping time. Slides will be posted online. Signal planes are used for connecting many routes at once without being just a wire. It's a two-dimensional thing connecting up many different points. Thermal relief, you have to make sure to leave a space from copper between point to point, or else your soldering iron is going to wick away heat too fast. Or the copper will wick away heat from the soldering iron too fast. Silk screen is important to keep proper labels on your board. Attentive vias and polar layouts, you guys don't know about it. Make sure all of your clocking is laid out very close to the area where it's clocking, okay? Clocks are high frequency signals. Often I see boards go bad because they didn't properly lay out their clocks. I see this all the time. So if you have a clocking signal coming in, you want to put all your chips that are being clocked by that clock as close as you can to that area. You don't want it to go a far way away. The farther it goes, the less signal integrity that you have. Okay? Decoupling capacitors, but we've kind of nailed that point into the ground if you guys don't understand it by now. All right, that's it. If your clicker ran out of batteries halfway throughout lecture, come talk to me because you're not going to get counted for attendance.